We'll begin section 15.6, talking about applications of surface integrals, and in particular, the topic of flux. Before we get into flux, we need to first understand a little bit of terminology regarding surfaces. Definition: a two-sided surface is said to be orientable, and a one-sided surface is said to be non-orientable. So what exactly does this mean, a one-sided surface versus a two-sided surface? So let's sketch a couple of examples that you're probably familiar with. Let's start with an orientable surface. All right. So this is going to be something that is two-sided. So probably our most common orientable surface would just be a sphere. If I said that some insect was walking on the outside of the sphere, you would know exactly what I meant versus the inside of the sphere. So the sphere is orientable. There are two sides to it. What about a non-orientable surface? We don't think about these quite as often. Let's draw an example of a non-orientable surface. So probably the most common non-orientable surface is the Mobius strip. So start by drawing an X, but make sure that one side goes behind the other so you can see that gap there, and then connect it around, and it looks like a rubber band with a half twist in it. All right. So here's the Mobius strip that has an umla over the O. All right. And this Mobius strip is non-orientable. And the reason is, if you were a little ant, let's draw a little ant here. This is about the extent of the artwork that we're doing. Let's say that we were coming around here, walking around this Mobius strip. And so right now it looks like you're on what we would say is the outside, right? What we would like to say is the outside. So we're going to walk around the back and we're still seemingly on the outside until we come back around to this other side. So we still appear to be on the outside. But as we continue to traverse in this direction, all of the sudden we're going to flip and we end up being on this backside. So I'll draw it kind of in red and hollowed out, that once we pass through that little half twist, we're no longer on that same part that we were walking on. We're now what appears to be the backside. But really, you can't say a side because we could continue this process for an eternity, and this ant would keep going back and forth. And the reality is, it's one-sided. It is not a two-sided surface. So that's an example of a non-orientable surface. For this section, we are only going to concern ourselves with orientable surfaces. So surfaces like the Mobius strip are out the window. And by the way, if you wanted to learn a little bit more about non-orientable surfaces, you need only Google Mobius strip or Klein bottle are both very classic examples of non-orientable surfaces. All right, so first let's talk about a surface that is given parametrically. So we've seen this type of a setup for a surface R where we have component function X in terms of U and V, Y in terms of U and V, and Z in terms of U and V. In section 14.4, we discussed how to compute surface area via double integrals. And um, what we did when we worked on that section was we defined the unit normal vector for a surface that's given parametrically. And so what we did was we took the cross product of your parametrization R with respect to U and V and then divided by its magnitude. All right. What we didn't talk about was the orientation of this normal. So we're going to say that n points in the positive direction and thus defines a positive orientation, and negative n points in the negative direction, thus defining a negative orientation. So remember that the cross product has the property that if you change the order, it negates the output. So the order of that output is important if you're looking for a positive orientation. All right, so now we would like to define flux, right? That's our main topic of this section. So we have informally the flux of an incompressible fluid moving freely through a permeable surface can be thought of as the volume of fluid that passes through the surface in 1 unit time. All right. So, what I like to think of is, for example, if you're brewing a beverage, whether it be tea or coffee, and whether it be the old fashioned way with a filter or whether it be with like a K cup brewing pod, all of those things have filters in them so that the coffee grounds or the tea leaves don't get into your drink. And so, that filter is a permeable surface, and typically, we're putting water through the filter, which is an incompressible fluid. And so, if you think of that analogy, what we're computing is how much of that fluid, in this case, water that's turning into tea or coffee, can pass through that filter in a given unit of time, whether that be a second or a minute, whatever that might be. So that's what flux is. We would like to determine how to use calculus to compute flux. All right, so we have now suppose that the velocity of the fluid at a given point xyz on the surface sigma is given by this vector field F. Notice that we have lowercase component functions f, g, and h. And suppose that n is the unit normal toward the positive side of sigma at xyz. Then the flux of F across sigma, denoted by the Greek letter capital phi, is given by phi equals the surface integral over sigma of F dot n ds. All right. So I just want to specify here that we're talking about a surface integral, which we just learned how to compute those in the last section. All right, so the question becomes, how do we express the normal vector of a given surface, right? That vector field F will be given to us. That's that velocity function. But it's our duty to come up with this normal vector based on our surface so that we can carry out this surface integral. All right, so recall from section 3.6 that for surfaces expressed in rectangular coordinates, the gradient was the key, right? The gradient vector is always perpendicular to the surface. So this brings us to our first theorem. All right, so this says, let sigma be a smooth surface of the form either z as a function of xy, y as a function of xz, or x as a function of gy. We can have it in any of these setups. And suppose that the component functions of the vector field f are continuous on your surface. Suppose also that the equation for sigma is rewritten as g of xyz equals 0 by taking g to the left side of the equation. Now let me pause here. That seems like not that big of a detail, but it's very important, so I'm going to highlight it. By taking g to the left side of the equation. So what this means is all these little g functions are moving over with that singleton variable so that the right-hand side becomes 0. If you do it the other way, you're going to have the negative gradient, which is going to lead you to the wrong answer. So I just want to call that to your attention. All right, and finally, and let R be the projection of sigma onto the coordinate plane by the independent variables of G. So here again, if you have Z as a function of XY, then you're going to project onto the XY plane. If you have Y as a function of XZ, then you're going to project onto the XZ plane, so on and so forth. If sigma has positive orientation, so again, here's that clause about keeping track of signs, then the surface integral f dot n ds can be expressed as the double integral over the region R of f dot gradient g dA. All right, so we're avoiding going through the agony of computing the surface integral, and instead we're just going to compute a double integral in rectangular or polar coordinates, whichever one makes more sense given your circumstance. So let's take a look at problem 14. find the flux of the vector field F, which is y j hat plus k hat, across the surface sigma, defined to be the portion of the paraboloid z equals x squared plus y squared below the plane z equals 4, oriented by downward normals. Now, if you want, you can give a quick sketch here of your surface if you find it helpful. So they tell us it's a paraboloid, and then it's being cut off at z equals 4. So I'll just cut it flat straight across there. And what we see here is that our surface is z as a function of x and y. So that tells us that we're going to project downward onto the, and maybe I should label my axes here, x, y, z. We're going to project downward onto the xy plane. So if we project downward, we're just going to see this circle. And you'll notice that if we plug in 4 for z, it's a circle of radius 2. So just by looking at that, this is giving us a tip off that we're probably going to use polar coordinates since our region R is a circle in the xy plane. All right, but we're not there yet. So first, what we would like to do is we would like to compute this gradient g. Now remember, we wanted to bring lowercase g to the left-hand side. So we're going to look at z minus x squared minus y squared equals 0, and then compute the gradient. So gradient g is going to be a negative 2x, negative 2y, and a positive 1. However, there was an important statement here that this paraboloid is oriented by downward unit normals, right? So here's our unit normals. All right, so what are we to make of this? All right, if it's going downward, that is a negative orientation. This is bad. So to take care of this, we're going to use the negative gradient. So let's make a note. But since sigma is oriented with downward unit normals, we'll use n to be negative gradient g, which is 2x, 2y, and negative 1. All right, so we have our gradient g, we know f, that's given to us, and we have already sketched our surface with our projection. So we see what our region R is. Let's set up our flux. All right, phi would normally be the surface integral over sigma of f dot n ds. We're going to instead write that as f, which is 0, y, 1, dotted with our n, which is negative gradient g of 2x, 2y, negative 1, dA. And we'll come back to those limits of integration, but first let's set up our integrand. So what we get here is a 2y squared minus 1 dA. All right. So now let's go ahead and set up our integral. We will go ahead and make the transformation into polar coordinates. So we want the full circle. So we want our theta to run from 0 to 2 pi. And the radius of our circle is 0 to 2. And then let's swap out our y squared is going to become an r squared sine squared theta. And dA becomes an r dr d theta. So I'll do one more step here before integrating. Let's just distribute that r in. 2r cubed sine squared theta minus r dr d theta. All right, so now we're able to move forward with integrating with respect to r. So we'll have 1/2 r to the fourth sine squared theta minus 1/2 r squared, where r is ranging from 0 to 2 d theta. Certainly, if we plug in 0, everything drops out. So let's just plug in 2. So 2 to the fourth, 2, 4, 8, 16 divided by 2 is 8 sine squared theta minus 4 over 2 is 2 d theta. And next, let's take care of this sine squared. As a reminder, our half angle formula says that sine squared is 1/2 of 1 minus a cosine 2 theta. So I'm going to use that identity from trig here. The 1/2 is going to simplify with the 8 to a 4. So we have 4 times 1 minus cosine 2 theta minus 2 d theta. And let's do some simplification here. I have a 4 times 1 minus 2 simplifies to just 2. 2 minus, and then don't forget to distribute the 4 to the cosine. So 4 cosine 2 theta d theta. All right, and now we're in business. We can integrate with respect to theta. This is a 2 theta. I'm going to kick out a 1/2 due to that 2 theta. So that's going to make that a minus 2 sine 2 theta from 0 to 2 pi. This sine function dies at both 0 and 2 pi. So all that's left over here is 4 pi. All right, so the flux of this vector field across sigma is 4 pi units per time. All right, so this was an example of computing the flux where our surface was given to us in rectangular coordinates. Remember, we had that paraboloid z equals x squared plus y squared. We'd also like to be able to compute flux if our surface is defined parametrically. So let's take a look at that. So for surfaces defined parametrically, with a parametrization R of UV, we already noted that the the unit normal vector, we would divide by the magnitude, but any normal vector can be expressed as the cross product of the two partials of R with respect to U and V. And so our final theorem here for this section says if sigma is a smooth parametric surface, and we have the vector equation R of U of V, then if the component functions of your vector field F are continuous on sigma, and if n determines the positive orientation, so again, we're looking for that orientation, it's just something to be aware of, then the flux sigma, which is normally expressed as a surface integral, can now be expressed as a double integral over the region R of f dot that normal vector, which is the cross product of the partials. Here it's understood that the integrand on the right side of the equation is expressed in terms of u and v. So if you want, you can write a little subscript uv there. So just make sure all of your coordinates are in that setup. So let's take a look at 18. It says find the flux of the vector field as given across sigma in the direction of positive orientation. Okay, where sigma is the portion of the elliptic cylinder as given, where u and v are bounded between 0 and 5 and 0 and 2 pi respectively. So let's start by finding that normal vector n. which is the cross product of the partial derivatives. All right, so I'm going to set up my I, J, K across the top. Let's take the partial of r with respect to u. Notice in these first two component functions, there are no u's, so that becomes 0. And then, of course, the last component function, its partial is 1. And now let's take the partials with respect to v. So the partial of cosine is a negative sine. Partial of sine is cosine. And the partial of u with respect to v is 0. So let's compute this cross product. In the I hat component, if we strike through that row, we get 0 minus cosine v. So a negative cosine v. All right, next I'm going to write my negative here just so that I don't forget it. If I strike through this column, I get 0 minus a negative 2v. So a positive 2v, but here again, that negative because we moved on to the j hat component. And finally, if I cross through the k hat column, I'm going to get zeros in both diagonals. So we have found our normal vector. Now what we want to do is dot it with our function f. And the first thing that I want to note here is that f is a function of x, y, z. So what we need to do is we need to remember our component functions x, y, and z in the parametrization R and plug those in to our vector field here where we see y, y, x, and z. All right, so let's go ahead and do that. I'm going to set up my flux equation. I'm going to write this as the double integral over R of, first, my vector field f, but as a function of u and v. So instead of e to the negative y, it's e to the negative sine v. Negative y is just negative sine v. And then x sine z becomes 2 cosine v sine u. All right, so this is my vector field f evaluated at the component functions x, y, z. And then I want to dot it with that cross product that I just found, negative cosine v, negative 2 sine v, and 0. And I'm just going to write a dA, but here again, if you want to write uv down there, just to remind yourself that it's not dx dy or dy dx. All right, so let's carry out the cross product or the dot product first. So I'm going to get a negative cosine v e to the negative sine v. And then I'll get a plus because of the double negative, 2 sine squared v. And then notice that that last term just drops out because of the 0 in that normal vector. So I'll just write my dA. All right, so at this point, we're ready to set up. I want to just note here that our bounds on u and v determine that we're integrating over a rectangular region. And so Fubini's theorem tells us that we can carry out this integration in either order, du dv or dv du. So you can kind of pick. You'll notice that it truly doesn't matter based on the integrand because there are no u's. So the order of integration really doesn't matter. I will go ahead and just do a dv du. We'll get through the hairy integration first. So I'll put my u limits on the outside, my v limits on the inside, and I have my negative cosine v e to the negative sine v plus 2 sine squared v dv du. All right. So the first thing that I'm going to do here is I'm going to use that half angle formula again, just to simplify this sine squared. Remember, it kicks out a 1/2, which is going to cancel with that 2. So I have a negative cosine v e to the negative sine v. And then I have plus the 1/2 goes away, 1 minus cosine 2v. dv du. All right, those last two pieces of the sum can be integrated directly. The first piece, however, is going to require a substitution. Normally, I like to do u substitution, but since u is one of my variables being used, I'm going to use w as my new variable. So I'm going to let w be negative sine v. So I'm choosing what's in the exponential function. That forces dw to be a negative cosine v dv, which is convenient because we see that outside. So what I'm going to do here is I'm going to set up my u substitution. So I'll still have, excuse me, let me leave off my limits of integration for now. I'm going to write them as question marks, but I'll leave my e to the u here. E to the W, that is. And I still have my dw du. And then let's go ahead and just integrate these other pieces here. So the integral of 1 with respect to v is a v, and the integral of cosine 2v is a 1/2 sine 2v. So this is where v is running from 0 to 2 pi du. So again, the sine function dies out at 0 and 2 pi. So the only thing that is going to remain here is going to be this 2 pi. So we can also now carry out this integration with respect to w. That's just going to give me an e to the w back out. So I'm going to swap it back for the e to the negative sine v. This is from 0 to 2 pi. And then I have my 2 pi here, where here again, that's just coming from this right here. And don't forget that this is all being integrated with respect to u. So what we get here is the integral from 0 to 5 of e to the negative sine of 2 pi, that's e to the 0, and then minus another e to the 0 plus 2 pi. So you'll see that these are just going to cancel out. And then a du here at the end. Finally, I'm just integrating 2 pi with respect to u. That's a 2 pi u from 0 to 5, which leaves me with 10 pi. All right, so you can see that the setup is very similar. The difference here being how you're computing your normal. If it's in rectangular coordinates, you're using the gradient. If it's in parametric coordinates, you're taking the cross product of the two partial derivatives. But all in all, we're defining flux as a surface integral, but we're computing it as a double integral, which is really great because we just saw that surface areas or surface integrals can be rather hairy. All right, that's all for this time.